Tonight, we're not just looking at a planet. We're falling into one. Close your eyes for a second and picture it. You're dropping straight down through the clouds of Jupiter or Saturn, the way you might fall toward Earth, expecting that at some point, this wild plunge has to end. There has to be a ground, right? A surface. A place where you'd finally hit something. Because here's what nobody tells you. The schoolbook picture you grew up with, the one where the gas giants are drawn as big balls of gas wrapped around a neat hard core in the middle, you know the one. That simple cross-section with tidy layers, like a cosmic jawbreaker. It's comforting. It says, don't worry, the universe works the same way rocks do. So, let's start at the very beginning of this fall. You punch through the tops of the clouds, past the familiar banded storms. At first it feels almost normal. Denser air, stronger winds, more gravity tugging at you as you sink. You tell yourself that if you go deep enough, you'll eventually hit something solid, the way you would if you dove through Earth's oceans to the rocky seafloor. But the deeper you go, the more that picture starts to break. The pressure climbs to millions, then tens of millions of times what you feel at sea level. Temperatures soar past the surface of the sun's photosphere. Hydrogen, the simplest element in the universe, stops behaving like a friendly gas and turns into a shimmering, electrically conducting liquid metal. Ice, if it even exists down here, stops acting like anything you'd call frozen and becomes a super hot, super dense fluid. At what point do you say, this is ground? Where do you draw that line? That's the paradox sitting at the heart of every giant planet. We talk about cores like they're just oversized versions of Earth's iron heart, but inside Jupiter and Saturn, the pressures may exceed 70 million atmospheres, with temperatures of 20,000 degrees or more. And under those conditions, the very idea of a sharp, solid core starts to blur. Is there a compact ball of rock and ice? Is it dissolving, stretched out into a ghostly, diluted core that bleeds into a metallic hydrogen ocean? Or does matter here enter an entirely new regime where solid and liquid stop being useful words at all? Now let's begin the real journey. Because this fall will take you from familiar cloud tops to oceans of metallic hydrogen, past layers where helium might rain like molten glass, into regions where diamonds could form and then melt before they ever reach the center. And yet something is above the planets. Something is below them. The question is, what really waits in that deep, unreachable middle? We've never sent a probe all the way down. We never will. So how can we possibly know what happens in a place that would crush you into plasma long before you reached it? That's where this gets strange, and where missions like Juno and Cassini, lab experiments, and the tiniest wobbles in a planet's gravity field start to turn that childhood picture inside out. So here's the weird part. You can never stand on Jupiter, and yet we talk about its core like it's a place you could plant a flag and take a selfie. That's the paradox. In every textbook picture, there's this neat layered cutaway. Clouds, deeper clouds, and then a tidy little central core, usually colored bright yellow. You know the one. It makes the middle of a giant planet feel like a room you could visit if you just had a good enough spaceship. But if you try to land, there's no surface, just gas that thickens, then crushes, then turns you into a smear of plasma long before you reach that cartoon center. But why do we care what's down there if no one is ever going to see it? Because here's what nobody tells you. The core of a giant planet is not a trivia fact. It's the control room. Deep inside, where pressures climb to tens of millions of times Earth's atmosphere, and temperatures soar above 20,000 degrees Celsius. The behavior of that hidden region decides almost everything the outside world experiences. Jupiter's core region is probably larger than Earth itself. Not just heavier, bigger in radius. Inside that enormous volume, hydrogen is squeezed into metallic form, electrons rip free, so the whole layer conducts electricity like a liquid wire wrapped around the planet. That's what powers Jupiter's colossal magnetic field, which in turn shapes its radiation belts, funnels charged particles, and blasts its surroundings with invisible storms. Saturn does a similar trick and even adds helium rain falling toward its interior, releasing extra heat so the whole planet glows with more energy than it gets from the sun. Those magnetic fields and heat leaks don't stay politely inside the planet. They reach up along the orbits of moons, carving out safe zones and danger zones. They decide whether an icy world like Europa keeps a liquid ocean, or whether a moon's atmosphere gets stripped away. In other words, what happens in the core can decide whether there are places for life to exist at all. Now zoom out. These giants don't just sit in the solar system like background scenery. Their cores, and how fast they formed, control how they tug on the protoplanetary cloud, how they migrate, how they fling or shepherd smaller worlds. Change the core, and you change the whole layout of a planetary system. You might even erase Earth-like planets before they ever form. So, let's start at the very beginning of our descent. In the next part, we'll take that familiar outer picture of bands and storms, peel it back one layer at a time, and follow gravity down through crushing pressures into the strangest forms of matter we currently know how to describe. Before we fall through those layers, can we make a quick deal with you? If the idea of hydrogen turning into metal, of diamond rain falling through alien skies, of a core so deep that gravity itself reshapes matter is already tugging at your brain a little, tap the like button right now. Because here's what nobody tells you. That tiny click doesn't just flatter an algorithm, it actually buys us time inside this rabbit hole. You know the one. The long form. Wait, how does metallic hydrogen even work kind of dive that almost never makes it into a textbook diagram? When you like a video like this, the platform quietly decides that there is an audience for weird corners of astrophysics and planetary science. That means we can justify spending weeks chasing down obscure Juno gravity data or lab experiments that crush hydrogen to millions of atmospheres, instead of cutting the cool parts and keeping it shallow. So, if your mental picture of a planet is already starting to wobble, that's your cue. Hit like so we can keep breaking the flat, cartoon version of the solar system and replace it with something closer to what's actually happening out there in space. And while we're making this bargain, we want to hear from you. Imagine we hand you an indestructible probe. No limit. It can survive 70 million times Earth's atmospheric pressure, swim through metallic hydrogen, shrug off temperatures hotter than the surface of the sun. Which giant planet do you send it into, and why? Do you dive straight into Jupiter to chase that blurry, diluted core that Juno hinted at? Do you drop into Saturn to watch helium rain fall like glowing bullets toward the center? Or do you aim for Uranus or Neptune to swim through that super-hot ice mantle where water and ammonia behave like nothing on Earth? Tell us in the comments which interior you'd explore first, and what you'd want the probe to measure when gravity finally drags it toward the core. Now, if this is the kind of question that makes you pause your day for 20 minutes, you might want to stick around with us. Hit subscribe with the little bell so you don't miss what comes next. We're going to keep going, down into exoplanet interiors with iron oceans and glass rain, into collapsing stars where electron degenerate matter holds up an entire sun, into every extreme core we can reach with physics and a bit of imagination. Because once you start seeing planets as layered pressure machines instead of colored balls, It's very hard to go back. Now let's begin our actual descent. To understand the core, we have to start from the outside and fall inward, layer by layer. So before we dive into metallic hydrogen and melting diamonds, we have to pause on the picture that's already in your head. You know the one. The clean textbook cutaway of a giant planet that makes everything look so simple, you could explain it with a single crayon. In that picture, a gas giant is a perfect sphere sliced neatly in half floating on the page. Around the outside, there's a thin, bright band labeled atmosphere, usually with painted clouds swirling like a weather report. Under that, a big colored region, gas layer, sometimes tagged as hydrogen and helium. Go deeper, and the color suddenly shifts again into liquid layer, as if someone just flipped a switch from air to ocean. And right in the center, a tiny, perfectly round dot. The core. It's always drawn as a small, dark, incredibly dense ball of rock and ice, sitting there like the seed in a peach. Solid, obvious, unquestioned. If you've ever glanced at a poster of Jupiter in a classroom, that's probably the core you think you're falling toward. So, let's start at the very beginning of that mental descent. Close your eyes for a second and imagine you're holding a smooth glass marble that just happens to be Jupiter. Clouds painted on the outside, banded and beautiful. Now slice it cleanly in half. Inside you see concentric shells. First the atmosphere, then deeper gas. Then a sharply defined boundary where a solid sphere begins. No fuzziness, no ambiguity. Just a tidy little planetary jawbreaker. Because here's what nobody tells you. The way we usually line up the giant planets reinforces that same tidy story. We put Jupiter, then Saturn, then Uranus, then Neptune in a row, and the diagrams make them look like scaled versions of each other. 4 marbles of different sizes, each with an atmosphere on top, a gas layer below, a liquid layer under that, and a neat rocky or icy core in the middle, like they were all built from the same instruction manual. We even lean on metaphors that make this feel inevitable. We call them onions with layers you can peel, or we talk about slicing them like fruit to reveal the seed at the center. It's comforting. It suggests that if you've seen one interior, you've basically seen them all. And yet something is above the planets. Something is below them. Those diagrams quietly tell you that from the top of the atmosphere down to that core, nothing especially weird happens. Just gas, then liquid, then rock. A flat story. Static, ordered in the next part. We're going to press on that picture until it breaks and watch what spills out between those supposedly clean layers. So here's the twist. That neat interior cross-section you've seen 100 times? It's not a lie. It's a comfort blanket. You know the one? Pastel bands for gas, a clean blue shell for liquid hydrogen, a tidy yellow ring for ice and rock, and then a solid red circle labeled core. It feels safe because it behaves like a layer cake. You know where you are. You know where you're going. Because here's what nobody tells you. The most important things happening inside a giant planet are exactly what those diagrams smooth away. On paper, Jupiter looks like a building. Clouds on floor 1, molecular hydrogen on floor 2, metallic hydrogen on floor 3, core in the basement. But if you could actually fly a ship straight down, you wouldn't get a cheerful elevator voice announcing, "Now entering, liquid layer." Every kilometer, the rules would bend a little more. The gas would thicken. The difference between air and ocean would stop being obvious. Where exactly did you cross the line? Diagrams draw sharp borders between gas, liquid, and solid because our brains love crisp categories. Inside a giant planet, those borders fray. Hydrogen doesn't suddenly wake up one morning and decide to become metallic at a single depth. Under millions of atmospheres of pressure, it gradually changes character. Atoms push so close that electrons roam more freely, until calling it a gas or a liquid stops being useful. It's a conducting fluid that acts like a metal and a fluid at the same time. Which color band is that supposed to be? The same problem hits our idea of surface. Those textbook pictures quietly assume there's a clear place where atmosphere ends and planet begins, just like the sharp line between air and ground on Earth. But for Jupiter and Saturn, there is no solid floor waiting for you. The top is simply where the gas becomes thin enough that we can see it go down, and it just gets denser and hotter, with no instant splash into a global ocean. Even the core, the one part that's supposed to be solid, is losing its job description. Gravity measurements from missions like Juno suggest Jupiter's core might be diluted, spread out, partially dissolved into the metallic hydrogen above, not a marble at the center, but a blurry, ghost-like region where heavy elements fade into lighter ones. So where does the core end and the mantle begin? The planet refuses to answer. And this is only the start of the weirdness, because once we let go of those flat layers, we're forced to meet states of matter that don't fit our everyday boxes at all. Metallic hydrogen that behaves like a liquid wire, supersonic ice where oxygen atoms form a solid lattice, while hydrogen ions flow through like an electric current. If gas, liquid, and solid are the only floors you thought existed, what do you even call a place like that? In a moment, we're going to walk you into those in-between worlds and watch ordinary atoms break all the rules you thought they followed. So when we say we're going to the core of a giant planet, what are we actually talking about? Is it the densest region? The hottest region? The place where rock and metal hide? Or just the deepest layer our equations don't completely fall apart? On Earth, core feels simple. You picture a metal ball under your feet, iron and nickel wrapped in rock. You know the one. But inside Jupiter or Saturn, that tidy picture starts to melt. Because here's what nobody tells you. In a world made mostly of hydrogen and helium, the usual boundaries between atmosphere, mantle, and core blur into a gradient of pressure, temperature, and chemistry that refuses to stay in neat boxes. So we need to get precise. In this video, when we ask about a core, we're really asking three questions at once. First, what does the inside of a giant planet actually look like in layers? If you could slice Jupiter like a cosmic fruit, where would the fluffy clouds end? Where would the liquid hydrogen begin? And where would that strange metallic hydrogen shell give way to something denser, heavier, and more core-like at the center? Second, how did it end up that way? So let's start at the very beginning. Did these planets build rocky, icy kernels first, and then pull in gas from the solar system's primordial cloud? Or did some of them form more like miniature stars, collapsing directly out of gas with no clean, solid seed? That origin story matters, because it decides whether a core is a permanent anchor or a dissolving ghost, slowly mixing into the envelope over billions of years. Third, what exotic physics takes over once gravity has squeezed ordinary matter far beyond anything we can experience on Earth? Deep inside, hydrogen can turn metallic, ice can become supersonic, and electrons can form seas that conduct electricity like a planetary-scale wire. At that point, core isn't just a location, it's a laboratory for extreme matter. And we're not talking about one generic giant. We're going to compare different worlds. Jupiter and Saturn, the classic gas giants with enormous hydrogen envelopes and possible diluted cores spread over a huge fraction of their radius. versus Uranus and Neptune, the ice giants, where the dominant layer is a hot, high-pressure ocean of water, ammonia, and methane. And whatever core lurks below that is living in a completely different environment. Pattern interrupt. We've never drilled, landed, or swum our way down there. So how do we know any of this? Now, let's begin to pull on the clues. Tiny wobbles in a planet's gravity field measured by Juno and Cassini. Subtle twists in magnetic fields that betray metallic hydrogen shells. Lab experiments that squeeze hydrogen until it screams into a new phase. By the end, we want you to replace that simple ball-with-a-core picture with a dynamic, evolving interior where heat, chemistry, and gravity are constantly reshaping what the word core even means. To really understand those wild, shifting cores, we have to do something dramatic. We have to rewind the whole solar system, not by a few million years, by billions. Now, let's begin in a place that doesn't look like a solar system at all. No sun, no planets, no neat flat diagram, just a cold, dark molecular cloud drifting through space. You know the one, the kind of enormous, silent cloud you see in telescope photos, blotting out starlight like spilled ink across the Milky Way. This cloud is mostly hydrogen and helium, the two lightest elements in the universe, left over from the Big Bang. But hidden inside is a precious sprinkling of heavier elements: oxygen, carbon, silicon, iron, tiny grains of rock and ice, ash from earlier generations of stars that lived, exploded, and seeded the galaxy. Because here's what nobody tells you. Without those microscopic impurities, your giant planet cores never get started. For a long time, the cloud just drifts, chilled to just a few tens of degrees above absolute zero, barely moving. Then, something happens. A passing shockwave from a supernova or a slow gravitational nudge from nearby clouds pushes part of it over the edge. Gravity gets a tiny head start. That region begins to collapse, and as it falls inward it spins faster and flattens into a rotating disk, the solar nebula. So, let's start at the very beginning of planet building inside that disk. At first, it's just gas and dust, moving in nearly circular orbit around a forming sun. But those dust grains don't stay dust for long. They collide at walking speed, stick together with electrostatic forces, and grow into larger clumps. Millimeter grains become pebbles. Pebbles become boulders. Boulders become kilometer-scale planetesimals, big enough that their own gravity starts to matter. Now the game changes. Once you have planetesimals, they don't just bump, they pull. Gravity lets them sweep up more material, merge in slow motion crashes, and carve lanes through the disk. In the outer regions, where it's cold and the cloud's ices can survive, these bodies gobble not only rock and metal, but thick mantles of water, ammonia, and methane ice. Their cores grow fast, and this is where the seeds of giant planets appear. A rocky and icy embryo 10 times the mass of Earth can tug on the surrounding gas hard enough to hold on to it. Instead of staying a bare core like our world, it starts inhaling the nebula. A vast envelope of hydrogen and helium piles on, turning a solid ice rock heart into a gas giant. Those are the cores we're chasing, born from dust in a collapsing cloud, fattened in a flat disk, and then buried under so much atmosphere that the original solid may blur or even dissolve. So what happens to a core once it's trapped under millions of atmospheres of pressure? That's where things get strange. So to understand how those buried cores get that extreme, we have to rewind the tape, not to the moment the gas piles on, but to the moment the whole region of space starts to spin. Now, let's begin with something deceptively simple: rotation. Take a huge cold cloud of gas and dust in the galaxy. It looks quiet, in the picture in your head. But give it the tiniest nudge of spin, and gravity does the rest. As the cloud contracts, that slow turn speeds up, like a figure skater pulling in their arms. Same angular momentum, smaller radius, faster spin. Because here's what nobody tells you. Gravity doesn't just pull in. It also has to deal with this growing sideways motion. The result is that the collapsing cloud can't fall straight to the center. The material that's trying to orbit piles up into a broad spinning disk around the newborn sun, while only a fraction falls straight in. Seen from the side, that disk is razor thin compared to its width. From above, it's a bright whirlpool of gas and dust. This is the protoplanetary disk. Most of the mass is now in a flat, rotating plane, and the future planets are just tiny clumps inside it, surfing around in nearly circular orbits. But this disk is not the same everywhere. Close to the young sun, temperatures soar. Metals and rock can survive there as solid grains, but water, ammonia, and methane are blasted into vapor. Farther out, the light weakens, the gas cools, and different materials can suddenly exist as solids. It's like a series of invisible frost lines drawn across the disk. You know the one that really matters for giant planets. The snow line. Beyond a certain distance, water can finally freeze into ice, and so can a lot of other volatiles. Overnight, the menu of solid building blocks changes. Instead of just metals and rock, you get ice-coated grains, fluffy, sticky, and far more abundant. Would you rather build a planet out of bare dust, or dust plus a thick layer of frozen water? Beyond the snow line, cores can bulk up fast. More solid material means more collisions, more mergers, more gravity. Once a clump reaches several Earth masses, it doesn't just sweep up solids, it starts vacuuming gas. That's how Jupiter and Saturn likely formed, in the cold outer disk, where icy cores could grow quickly enough to grab huge envelopes of hydrogen and helium before the disk dispersed. And yet something is above the planets, something is below them. The way this disk flattened and cooled doesn't just set their orbits, it sets their internal layering. So what does that mean for the strange physics deep inside a giant's core? So, let's start at the very beginning of a giant. Not with swirling clouds of gas, but with something surprisingly small, grains of rock and ice quietly orbiting in that cold outer disk. Out here, beyond the young sun's glare, those grains collide. Gently at first, then harder. Pebbles become boulders. Boulders become mountain-sized planetesimals. Because here's what nobody tells you. Before you get a majestic gas giant, you get a brutal demolition derby of icy rubble, smashing together and merging into embryonic worlds called protoplanets. As these protoplanets grow, their gravity carves lanes in the disk. They hoover up nearby debris, clearing out gaps and feeding on anything unlucky enough to cross their orbit. In your textbook picture, the disk looks smooth and flat. In reality, it's pockmarked with these hungry seeds, each racing to bulk up before the clock runs out. Why a clock? Because the gas doesn't stick around forever. The young sun is blasting the disk with radiation and stellar winds, slowly blowing the nebula away. So each core is in a race, reach a critical mass while the gas is still there, or stay small forever. Hit roughly 10 Earth masses, and something changes. The core's gravity is now strong enough that it doesn't just pull in pebbles, it starts to pull in gas efficiently. A tiny atmosphere of hydrogen and helium forms, then thickens, then deepens. That atmosphere cools, contracts, and makes the gravity well even steeper, which lets it pull in more gas. Faster. This is runaway gas accretion. The more envelope the core gathers, the deeper its gravity well becomes, and the easier it is to grab still more of the nebula. What was once a modest ice rock ball suddenly inflates into a world tens or hundreds of times Earth's mass. If you could watch the disk and fast forward, you'd see a few of these seeds explode into giants while their slower neighbors are left behind as super-Earths or mini-Neptunes. Timing is everything. Miss the gas window by a few 100,000 years, and the disk is gone. The sun's winds strip the nebula, leaving your core wrapped in only a thin, high-metallicity atmosphere. Catch it just right, and you get a Jupiter, with enough hydrogen to crush its center to pressures tens of millions of times Earth's surface. And that growth history doesn't just change the outside. It rewrites the inside. A rapidly accreted, massive envelope can squeeze the core so hard that its outer layers dissolve, blurring the boundary between core and mantle into a diluted, mixed region. A slower, gentler build might leave a sharper, more distinct core buried beneath. So when we ask what really sits at the heart of a giant planet, we're not just asking about pressure and temperature. We're asking about its entire origin story, written in layers. Because the next question is brutal. After all that growth, does the core even still exist as a solid thing at all? So what if the answer to that brutal question is already written into Jupiter's gravity? Because here's what nobody tells you. We've been weighing Jupiter's insides, and they don't behave like a neat little metal marble at the center. NASA's Juno spacecraft has been flying tight, looping orbits around Jupiter, measuring the planet's gravity field to absurd precision. Tiny changes in Juno's speed as it swings past tell you how mass is arranged deep below the clouds. If Jupiter had a small, sharply defined core, the gravity signal would look one way. But it doesn't. The data point to something stranger, a core that seems extended, fuzzy, spread out over a huge fraction of the interior instead of being locked in a compact rock metal ball. So what could blur the heart of a world that massive? One leading idea is surprisingly violent. In the very early solar system, when Jupiter was still growing inside the protoplanetary cloud, a large protoplanet, maybe 10 times Earth's mass, could have slammed straight into it. Not a gentle merger. A catastrophic head-on collision. Picture that for a second. You know the one, the classic flat diagram of orbits. Everyone minding their own business in a tidy plane. Now tilt the camera. In three-dimensional space, a rogue core can come screaming in on a plunging path, fall into Jupiter's gravity well, and hit so hard it doesn't just sink. It shatters the original compact core, stirring it into the surrounding hydrogen-helium envelope like a rock thrown into molten glass. Instead of all the heavy elements staying locked in one dense sphere, the impact injects them into deeper layers, smearing them outward. You don't get a clean boundary between core and not core. You get a gradient. The deeper you go, the richer the mix of rock, metal, and ices, fading smoothly into the overlying metallic hydrogen sea. It's less a billiard ball and more a thick, murky region where composition changes with depth. And that's the real twist. A giant planet's core is not just a passive relic of formation, quietly sitting at the center while gas piles on top. It can be actively reworked by later impacts, then slowly reshaped again by long-term mixing and convection. Over hundreds of millions of years, gravity, heat, and turbulent flows can keep blurring that original core, turning a one-sharp boundary into a diffuse, diluted interior. So when we talk about the core of a giant planet from here on, we might not mean a simple solid sphere at all. We might mean a whole region where heavy elements gradually increase toward the center, a ghost of a core stretched out in depth. Now, let's begin to peel back those layers and see what that actually feels like as you fall inward. We've talked about this ghost of a core. Now let's begin where your eyes can actually land, the very top of a giant planet. You've seen the pictures. Jupiter's swirling bands, Saturn's golden belts, and that razor-sharp ring system slicing through space like a cosmic vinyl record. Zoom in and the cloud tops look almost painted on. Cream, rust, ochre, white. Storms the size of continents, curling and uncurling like slow-motion hurricanes. And then there's the celebrity. The Great Red Spot. You know the one. A storm wider than Earth, raging for at least 300 years that we've been watching, probably longer, with winds screaming around its edge at hundreds of kilometers per hour. Around it, delicate filaments of cloud twist and braid, like smoke in slow gravity. Because here's what nobody tells you. All of that drama you've seen in every textbook and documentary, that's not a surface. There's no ground there, no place to stand, no cliff edge, no top in the way we use that word on Earth. Those cloud tops are simply the level where sunlight mostly gives up, where photons coming in from the sun are scattered back into space so efficiently that, from orbit, that's what our cameras see, the bright, reflective skin of a vast, deep atmosphere. It's the outermost paint on a planet-sized storm. If you pick a reference level, planetary scientists often use the pressure where the air is like what you're feeling right now at sea level, about 1 bar. On Jupiter and Saturn, that 1 bar level sits roughly in the visible cloud deck. Temperatures there are surprisingly familiar too, somewhere around -100 to -150 degrees Celsius, depending on latitude and height. Cold, but not instantly turn you into plasma cold. Drop just tens of kilometers below those bright bands though, and the numbers start to climb. The pressure doubles, then triples. The temperature rises. The ammonia clouds you saw from orbit give way to deeper water clouds and layers rich in ammonium hydrosulfide. A chemical cocktail that would make Earth's worst thunderstorm feel like a polite drizzle. Weather here is driven from both sides. Sunlight heats the upper layers, while internal heat leaking out from the deep interior churns the atmosphere from below. Jets and vortices form where those influences collide, carving the neat dark belts and pale zones that wrap around the planet. It looks wild. It is wild. But compared to what waits deeper in, this is still the gentle part. Up here, hydrogen and helium behave like the gases you're used to. Clouds are clouds. Lightning is lightning. You could, in principle, imagine a balloon floating for a while before the pressure crushes it. And yet something is above the planets. Something is below them. From this photogenic, almost familiar layer, we're about to fall into regions where hydrogen stops acting like a gas at all, and even the word cloud stops making sense. So, let's start at the very beginning of that descent. The moment those pretty bands vanish behind you, and the atmosphere stops caring that you once lived on a rocky world. Down here, the idea of air starts to break. Fast, as you drop below the last sunlit clouds, the pressure climbs from a few bars to tens, then hundreds. Within a couple of thousand kilometers, you've gone from something your lungs would hate to something no lung has ever met. Hundreds of times Earth's sea level pressure, then thousands. Temperatures that were a few hundred degrees near the cloud tops surge into the thousands. You are falling into an atmosphere that is acting less like sky and more like an ocean turned vertical. Because here's what nobody tells you. The atoms haven't changed. It's still hydrogen and helium, the same simple elements that fill stars and drift in the interstellar cloud between them. But under this much gravity, they're packed together so tightly that the old categories stop working. Gas? Liquid? Those words belong to the surface world you came from. Now, let's begin to talk about what they become instead. As the pressure and temperature rise together, hydrogen and helium slide into what physicists call a supercritical state. There's no sharp boiling point, no dramatic moment where bubbles form and say, "Now I am a liquid." There is just a smooth, relentless thickening. With every kilometer, the density increases, the fluid gets heavier. The way water feels thicker than air, except here, the change is continuous, with no clean boundary. So, let's start at the very beginning of that transformation. Imagine looking for the surface of a gas giant the way you'd look for a shoreline. You know the one, a crisp line where blue ocean ends and brown land begins. Down here, that line never appears. Instead, the transparent upper atmosphere slowly turns hazy, then milky, then into a dense, churning supercritical fluid of molecular hydrogen and helium. It behaves like an ocean, but an ocean that never quite decides where it starts. In this regime, the usual rules you learn from weather forecasts begin to fail. What does a cloud even mean when there's no clear top or bottom? Just regions where droplets and crystals form inside a medium that isn't really gas or liquid. What does floating mean when everything around you is compressible, and the difference between light and heavy is being rewritten by pressure you can barely imagine? And yet something is above the planets. Something is below them. Up here, storms still have tops and bottoms. Down there, buoyant plumes and sinking currents twist through a planet-wide ocean of supercritical hydrogen, guided by heat from below and rotation from the planet's orbit around its axis. It's familiar convection in a profoundly unfamiliar phase of matter. If the line between atmosphere and interior is already this blurry, what happens when the hydrogen itself changes identity, turning from this dense, invisible ocean into something that behaves like liquid metal? That's where we're heading next. Down here, hydrogen doesn't just get denser, it changes identity. Keep sinking through that deep, dark ocean of compressed gas, and you eventually hit a threshold where the rules you use to just stop working. At around 1.4 to 3 million times Earth's atmospheric pressure, the crush of gravity forces hydrogen atoms so close together that their electrons become delocalized. They're no longer politely orbiting individual protons. They're roaming freely, forming a sea of charge that can slide and flow. In other words, hydrogen starts behaving like a metal. But this isn't a shiny solid bar you'd hold in your hand. It's a liquid, a conducting fluid. Imagine a planet-sized ocean of liquid metal, wrapped around the deeper core like a glowing, invisible shell. In Jupiter and Saturn, that metallic hydrogen layer probably takes up the bulk of the interior volume, a thick mantle of alien water with no surface and no shore. Because here's what nobody tells you. The most important part of a gas giant isn't the visible atmosphere you see in pictures. It's this hidden metallic ocean, humming away in the dark. And it's not just sitting there, it's moving. Hotter metallic hydrogen from deeper down rises. Slightly cooler fluid from above sinks. That convection, twisted by the planet's rapid rotation, turns the whole layer into a gigantic electrical generator. You know the one, the dynamo. Charged particles are dragged through magnetic fields, which then strengthen and organize those same fields, in a feedback loop that can run for billions of years. This is how Jupiter's magnetic field becomes so intense it would fry your electronics long before you ever saw a cloud. Temperatures in this zone reach tens of thousands of degrees. Densities rival those of solid metals on Earth, even though the material is still fluid enough to churn and roll. It's like having an iron core that can boil. That contrast is hard to picture from our quiet, rocky perspective on the solar system's outer edge, where metal means solid and ocean means transparent blue. down here, both ideas merge. Pattern interrupt. Forget the cartoon of a tiny marble core with gas gently resting on top. The weight of this metallic hydrogen shell is enormous. It presses inward on whatever lies beneath: ice, rock, a diluted mush of heavy elements, with pressures that eventually climb tens of millions of times Earth's air pressure. That squeeze can dissolve parts of the original core, blur its boundaries, and even change which exotic phases of matter can exist there. Now, let's begin to turn our focus even deeper. If the metallic ocean is this extreme, what happens in the region it's crushing? The place where core stops being a simple word and becomes a whole new kind of interior world. To answer that, we're going to cheat a little. We're going to step sideways from the generic giant planet and drop into a very specific one: Saturn. You know the one, the elegant ringed world that looks almost delicate from a distance. On the outside, Saturn is pale, hazy, almost calm. But far below those calm cloud bands, there's a kind of weather that makes hurricanes look boring. It's not wind. It's not rain like you know it. It's helium. Because here's what nobody tells you. Deep inside Saturn, hydrogen and helium don't always play nicely together. Under the insane pressures where hydrogen has turned into a metallic, electrically conducting liquid, the mix becomes unstable. At certain temperatures and pressures, helium stops dissolving evenly in that metallic hydrogen ocean and starts to separate out, the way oil separates from water when you let a salad dressing sit. Now picture this. Within that metallic layer, tiny droplets of nearly pure helium begin to form. Real droplets. A hidden storm of liquid helium condensing out of the mix. Those droplets are denser than the surrounding metallic hydrogen, so gravity does exactly what you'd expect. They fall. They fall for tens of thousands of kilometers, sinking toward the core like a slow, silent rain. This is helium rain, and it's not just a poetic phrase. As those droplets sink, they lose gravitational potential energy, and that energy has to go somewhere. It turns into heat, warming the deep interior. Saturn, in other words, is being heated from the top of its core region downward by a rain of helium from above. That extra heat leaks outward over millions of years, so Saturn glows in infrared with more energy than it gets from the sun. The planet is literally brighter on the inside than you'd expect from sunlight alone. So, let's start at the very beginning of the impact this has on the structure. When helium rains out of the upper layers, it leaves them relatively poorer in helium and enriches the deeper regions. You end up with a composition gradient: lighter, helium-depleted fluid above, heavier, helium-rich fluid below. That can muffle simple, boiling pot convection and replace it with more complex, layered motions, like a stack of slowly mixing oceans instead of one big churning pot. In a world built on convection, that changes how heat escapes, how the magnetic field behaves, even how the core evolves. And yet something is above the planets. Something is below them. For Saturn, above the core isn't just metallic hydrogen, it's an active conveyor belt of helium raining down, feeding the deep interior. The core region isn't a static pile of ancient rock and ice. It's being resupplied, reshaped, and reheated by material falling out of the layers overhead, which raises a bigger question. If Saturn's core is being rewritten by helium rain, what does that say about the cores of other giants, where the ingredients and weather are even stranger? If Saturn's core can be edited by helium rain, what happens when the whole planet is built from different ingredients in the first place? To really test what a giant planet's core can be, we have to leave the gas giants behind and head for the misnamed outsiders of the solar system, the ice giants. Uranus and Neptune. You know the one textbook label that's been stuck on them for decades. Ice giants. It sounds like they should be colossal snowballs, frozen solid in the dark. But they're not, because here's what nobody tells you. On these worlds, the ice is hot. It's crushed into bizarre fluids under pressures millions of times higher than what you feel at sea level on Earth. So, let's start at the very beginning of their interior. If you could dive through Uranus's blue-green clouds, the first layer you'd pass is actually familiar from Jupiter and Saturn, a relatively thin envelope of hydrogen and helium, just a few Earth masses worth, spread over a huge volume. It's the visible face, the postcard picture. Under that, the planet changes character fast. You hit the mantle. This is where ice stops meaning what your freezer makes and starts meaning water, ammonia, and methane in any condensed form under ridiculous conditions. Temperatures climb to thousands of degrees. Pressures soar to hundreds of gigapascals. The molecules don't behave like a liquid, or a solid, or a gas in any normal sense. They enter supercritical and exotic states, where there is no clear boundary between liquid and vapor, just a dense, churning ocean of molecules slamming into each other. Push deeper, and water itself can turn supersonic. Imagine a crystal lattice of oxygen ions locked in place, like a solid, while hydrogen nuclei, bare protons, flow through that lattice like an electrical current, part solid, part liquid, part conductor. It sounds like science fiction, but high-pressure experiments and simulations keep pointing to this strange phase inside Uranus and Neptune. You're not swimming in this layer. You're being dissolved in a planetary-scale battery. And that battery matters, because this mantle is probably where their magnetic fields are born. Unlike Jupiter's field, which is roughly aligned with its rotation axis, Uranus and Neptune have magnetic fields that are wildly tilted and offset, as if someone shoved the magnet out of the center and twisted it sideways. A thin dynamo shell in that supersonic conductive mantle can naturally give you a lopsided, patchy field. The result is a magnetic map that looks more like modern art than a tidy bar magnet. Deeper still, gravity pushes you toward a dense rock metal core. Here, the boundary between mantle and core may be sharper than Jupiter's blurred, diluted interior. But don't picture a calm, cold ball of granite. At tens of thousands of degrees, under crushing pressure, even rock is a high-pressure fluid or exotic solid, far from anything you'd stand on. And yet something is above the planets, something is below them. If the ice giants can twist magnetism and matter this far, what happens in worlds even stranger, where the line between core and mantle disappears completely? So, if rock is already misbehaving, what happens when you take something even more familiar and push it past the breaking point? You get a world where it literally rains gemstones, where the phrase diamond in the rough is just the weather report. Because here's what nobody tells you. Inside planets like Uranus and Neptune, the word ice stops meaning what you think it means. Their mantles aren't polite white crystals. They're hot, dense oceans of water, ammonia, and methane, crushed under millions of atmospheres of pressure. In lab experiments, we've tried to recreate those conditions, and the results are ridiculous. You take methane, CH, the simple molecule you'd find in a gas stove. You squeeze it with shock waves and laser pulses until the pressure is millions of times Earth's atmosphere and the temperature soars to thousands of degrees. And then the molecule just gives up. The carbon and hydrogen split. The carbon atoms link up. And out of this chaos, tiny diamond crystals appear. In a flat classroom diagram, methane is just a label in the ice layer. In the real three-dimensional planet, it's raw material for an endless diamond factory. Now scale that up to a whole mantle. You know the one. those blue-green ice giants sitting quietly at the edge of the solar system. If diamond forms deep in their interiors, it doesn't float. It sinks. Imagine diamond rain, glittering crystals falling through a hot, dark ocean of exotic fluid, piling up into layers or even slushy oceans of diamond at certain depths. On Uranus and Neptune, the most precious gemstone you can think of might be as common as sand on a beach. Pattern interrupt. This isn't just about making sci-fi jewelry. Those falling diamonds carry heat and energy. As they form and sink, they release gravitational energy, stirring the mantle, driving convection, and changing how heat moves toward the core. The deeper you go, the stranger it gets. Because water itself rebels. Under even more intense pressure and temperature, experiments suggest it becomes supersonic ice. In this phase, the oxygen atoms lock into a crystal lattice, like a solid, but the hydrogen ions roam through that lattice like a liquid. It's both rigid and flowing at the same time. Is it a solid? Is it a liquid? The answer is yes. Supersonic ice is also highly conductive. Those migrating hydrogen ions can carry electric current, which means a thick shell of this weird ice can help power a global dynamo. That's one reason Uranus and Neptune have such twisted, off-center magnetic fields. Their conducting, convecting mantles are doing the job that metallic iron does inside Earth. So if the ice layer is a storm of diamond rain and supersonic lattices, what does that say about the true core buried below? At this point, are we talking about rock and metal at all? Or something so dissolved and blended into the mantle that the old picture of a neat, solid center just falls apart? So that old, comforting picture of a neat marble at the center? The place where you land your ship, step out, and plant a flag? That's the part that really breaks. Because here's what nobody tells you. For Jupiter and Saturn, there is no ground in the way your brain wants there to be. You fall through clouds, then thicker clouds, then fluid so dense it feels like diving into liquid metal. The pressure climbs to millions of atmospheres. The temperature races past thousands of degrees. And long before you reach anything rigid, your probe, your ship, your heroic sci-fi space boots are just plasma. Now, let's begin with Jupiter, since it's the one you've seen in every solar system poster. You know the one. Swirling bands, great red spot. A place you imagine a floating city hovering just above the storms. If you try to descend, there's no sharp line where atmosphere ends and surface begins. The gas just gets denser, then turns into a hot, compressible ocean of hydrogen, then into that metallic hydrogen shell we talked about. All the while, gravity squeezing you harder than any lab on Earth can reproduce. Deep in the very center, there probably is a region of rock and metal, not like Earth's crust, but a core crushed to incredible densities, perhaps mixed with ices and exotic phases, maybe even arranged in crystalline lattices that only exist at tens of millions of atmospheres. But here's the catch. That solid is buried under tens of thousands of kilometers of fluid envelope. You don't stroll down there. You don't stand on it. You are part of the experiment it is running on matter itself. Saturn plays the same game, just a little more politely. Lower mass, slightly lower pressures, but the same basic story. No solid surface, just deeper and deeper layers until you reach a core region that's more like a compressed alloy than a floor. If there's a boundary, it's defined by composition and density, not by anything a human foot would recognize as ground. What about Uranus and Neptune? They sound more promising, right? Ice giants. Icy cores. Surely that means something you could, in principle, stand on? Here the transition from that supersonic, electrically conducting ice mantle to a rock metal center might be sharper, more like a sudden change than a long blur. But the conditions are so extreme, that standing stops being a meaningful concept. At millions of atmospheres and thousands of degrees, you aren't a person on a surface. You're matter in a phase diagram. So when planetary scientists say core, they're not picturing a cavern you could explore. They're drawing a boundary in a model. Here the mix is heavier elements. Here the density jumps. Here gravity and pressure have rewritten the rules. And yet something is above the planets. Something is below them. Layers upon layers, all the way down to a center no human will ever visit directly. Which raises a deeper question. If we can never go there, how do we know those hidden interiors aren't completely different from the picture we've just drawn? So if we can't dig a tunnel into Jupiter, how do we know what gravity, pressure, and temperature are really doing down there? We start with something you do understand: weight. So, let's start at the very beginning. Imagine stacking mattresses on a bed. 1, 2, 10, 50. The one at the bottom doesn't just feel its own weight. It feels the weight of every mattress above it. Now stretch that picture from your bedroom to a sphere tens of thousands of kilometers deep. Inside a giant planet, every layer is supporting the weight of all the layers above, pulled inward by crushing gravity. Because here's what nobody tells you. Pressure isn't some abstract number in a textbook. It's literally how hard each layer is being squeezed by everything sitting on top of it. Near the cloud tops, the mattress stack is light. Drop 1,000 kilometers, and the stack has grown. Drop 10,000, and the pressure has climbed to millions of times what you feel at sea level on Earth. Keep going toward the core, and you reach tens of millions of atmospheres. The bottom mattress is now under a skyscraper made of planet. When you compress gas like that, you don't just make it denser, you heat it. As particles are forced closer together, they collide more, bounce harder, and their average energy goes up. That's temperature. If energy can leak away into space, the gas cools. But deep inside a giant planet, radiation has a long, hard journey out, so the heat gets trapped, and the interior bakes itself from the inside. This is why Jupiter's center may be over 20,000 degrees Celsius, hotter than some parts of the sun's surface. Even though it's just orbiting quietly in the solar system like a normal planet, Saturn is still glowing with leftover heat and helium rain because its interior is so squeezed that it can't easily get rid of energy. Now push that compression further, and something stranger happens. Bonds break. Atoms rearrange. Under a few million atmospheres, hydrogen stops behaving like the familiar gas you breathe about in chemistry class and starts acting like a liquid metal, with electrons roaming freely. Water, ammonia, and methane in ice giants are forced into exotic superionic phases, where oxygen atoms sit in a lattice, while hydrogen atoms buzz through like an electrical current. The core region is where all of this goes to the extreme, where pressure and temperature shove matter into regimes we can barely reproduce on Earth, even with our most powerful lasers and diamond anvils. And yet, something is above the planets. Something is below them. Above, ordinary clouds and winds. Below, this hidden, boiling hierarchy of phases and crushed atoms. So here's the real twist. If gravity can rewrite the rules of matter this much, what else might it be doing to the very heart of these worlds that our current picture still gets wrong? So let's follow gravity all the way down and see what that does to Jupiter's heart. Not the pretty cloud tops, the place where numbers stop feeling real. Near the center of Jupiter, the pressure isn't just high, it's absurd. We're talking tens of millions of times Earth's atmospheric pressure, climbing toward around 70 million atmospheres in the deepest regions. Because here's what nobody tells you. That's not just crush a submarine pressure. That's squeeze every known material into bizarre, exotic states pressure, where even the word solid starts to lose its usual meaning. Now, let's begin to layer in the heat. At those depths, temperatures are estimated to exceed 20,000 degrees Celsius. Hotter than the surface of the sun you see in all those textbook diagrams. Imagine being inside a planet and yet feeling like you've fallen into a star's outer skin. Down there, the distinction between gas and liquid melts away, and the core region becomes a seething, plasma-like ocean of particles. Density follows suit. The material near Jupiter's center is thought to pack in at several times the density of rock. Hydrogen and helium, the same simple gases that give you gentle auroras and fluffy solar system illustrations, are hammered into forms far denser than anything you can encounter naturally on Earth. You know the one, that mental picture of hydrogen as the lightest, most delicate element. Inside Jupiter, gravity tears that picture to shreds. Under those pressures and temperatures, atoms themselves start to unravel. Electrons are stripped from their home orbits, turning the interior into a partially ionized soup where electrons are free to roam. Standard chemistry, the kind you learned in school with neat shells and tidy bonds, just stops working the way it's supposed to. You don't really have molecules in the normal sense. You have a crowd of nuclei and electrons jostling through a metallic, electrically conducting fluid. Here's the pattern interrupt. We still call this a planetary core, as if there's a clean, solid ball sitting there like an oversized marble. But in these conditions, the boundary between core and mantle can blur into a gradient of crushed ices, dissolved rocks, and metallic hydrogen, all mixing and flowing under impossible pressures. It's less a billiard ball, more a roaring, half-melted heart. So that raises an uncomfortable question. With pressures that would pulverize any probe, temperatures that outshine the sun's surface, and chemistry that refuses to behave, how can we possibly know what's really happening down there if no instrument can survive the journey? What kind of tricks do we have to use to turn that invisible, unreachable core into a picture we can trust? So how do you spy on a core you can never visit? You don't dig. You listen. You watch how the whole planet moves, wobbles, and rings like a buried bell in deep space. Because here's what nobody tells you. A planet's gravity isn't smooth. It's lumpy. If the mass inside were perfectly uniform, the gravity field would be perfectly simple. But real giants hide dense cores, flowing metallic hydrogen, and swirling ice layers, and each of those leaves a tiny fingerprint in the gravity field. A heavier core pulls a little harder. A stretched, diluted core pulls in a different pattern. Those patterns are what we hunt. Now let's begin with the easiest thing to measure from far away: how a spacecraft falls. When Juno dives past Jupiter, or when Cassini skimmed over Saturn's rings, they weren't just taking pretty pictures. They were radio beacons. As they flew through the changing gravity field, their speed changed by just a few millimeters per second. From Earth, we tracked the Doppler shift in their radio signals, watching the pitch slide up and down as gravity tugged on them. It's the same principle as a passing siren, but stretched across hundreds of millions of kilometers. Those tiny shifts let us map where gravity is a little stronger or weaker, a little off from what a perfectly smooth planet would produce. From that, we back out how mass must be arranged inside. Does Jupiter's gravity look like it has a compact, bullet-like core? Or does it look more like a blurry, diluted cloud of heavy elements spread through the inner half of the planet? Juno's measurements pushed us strongly toward that second, weirder picture. Gravity isn't our only spy. Giant planets also hum. They have quakes and global oscillations, waves that travel through their interiors and make the whole planet subtly expand, contract, and ripple. The frequencies of those waves depend on how density and composition change with depth, just like the pitch of a drum depends on its size and what's inside it. Planetary seismology is the art of turning those pitches into a 3D interior map. But how do you hear a planet with no solid surface full of seismometers? For gas giants, we cheat. Saturn's rings, for example, feel every tiny oscillation in the planet's gravity. Certain ring particles bunch into spiral patterns because the planet beneath them is pulsing. Read the patterns, and you read Saturn's internal vibrations. With Jupiter, we also watch subtle pulsations in the cloud tops, tiny changes in brightness and motion that betray waves echoing through the metallic hydrogen below. So, let's start at the very beginning of how we test our ideas. We build models of possible cores, run simulations of how those interiors would bend gravity and shape waves, and then compare them to what Juno, Cassini, and the rings actually show us. The models that match survive. The ones that don't get thrown out. And yet something is above the planets. Something is below them. In the next part, we're going to follow those clues all the way down, layer by layer, to see what kind of core could create such strange signals. So if gravity and waves tell us the shape of the deep interior, the next question is brutal and simple. What is it doing down there? Not just where the layers sit, but how they move. Because here's what nobody tells you. When a giant planet draws with magnetism, it's sketching a self-portrait of its core. Magnetic fields on worlds like Jupiter and Saturn aren't painted on like stripes. They're generated in real time by moving, electrically conducting fluids deep inside. You take a region where hydrogen is squeezed into a metallic liquid, or ices are crushed into strange superionic phases, spin the whole planet, stir those layers with convection, and you get a dynamo. Map that magnetic field from orbit, and you're effectively tracing where those conducting layers are and how they flow. Juno did exactly that at Jupiter. It didn't just fly by the cloud tops, the one from every solar system poster. It dove through the planet's magnetic bubble over and over, measuring tiny twists in the field. If Jupiter were a simple bar magnet, the map would be boring. Instead, Juno found weird patches, hot and cold spots in magnetism, and asymmetries between north and south. There's a particularly intense region near the equator nicknamed the Great Blue Spot. What could carve a magnetic bruise like that into space? The best explanation is messy, layered motion in Jupiter's metallic hydrogen shell. The dynamo doesn't sit in a thin, tidy band. It's spread through a deep, turbulent ocean of liquid metal, with flows that speed up, slow down, and shear past each other. Those motions twist magnetic field lines, bunch them up, and tangle them in ways that only make sense if the conducting region extends surprisingly far out from the core, blending into that diluted inner mantle Juno's gravity data hinted at. Now compare that to Uranus and Neptune. Their magnetic fields are tilted by 50 to 60 degrees from their spin axis and offset from the center. It's like someone took the usual dipole, kicked it sideways, and slid it off the core. That tells us their dynamos probably don't live in a deep central shell at all, but in a shallower layer of superionic water, ammonia ice, wrapped around a smaller, perhaps sharper core. Same basic physics, completely different geometry. And this is where depth matters. The radius where the dynamo seems to operate pins down where hydrogen must be metallic, or where exotic ices must conduct. If the field is generated very deep, the metallic layer hugs the core, and the core can be relatively large. If the field comes from higher up, the core might be smaller, or partially dissolved into a broader conducting mantle. Every magnetic wiggle is a constraint on core size and composition. Now let's begin to put the pieces together. Gravity tells you where the mass is. Magnetism tells you which parts of that mass can carry current and how they're churning. Combine them from Juno, Cassini, and Voyager, and you get a three-dimensional, time-evolving picture of what's happening around and within the core, even though no probe has ever been there. But there's one more clue hiding in plain sight, written not in fields or waves, but in heat. To see it, we have to follow the energy leaking out of these planets and ask a much more uncomfortable question. What exactly is the core doing to stay so hot for billions of years? To answer that, we have to do something a little insane. We have to build a tiny fake Jupiter on a lab bench. Now let's begin with the most delicate torture device in high-pressure physics, the diamond anvil cell. Picture two flawless diamond tips facing each other, with a microscopic sample of hydrogen or planetary ice trapped in between. As we crank the anvils together, that little pocket of matter is squeezed to millions of atmospheres of pressure, far beyond anything on Earth's surface. It's the same basic ingredient you find in Jupiter's deep interior, gravity, turned into pure compression. Because here's what nobody tells you. When you're trying to understand a giant planet's core, you don't just need a big telescope. You need a really good vise. The diamond anvil cell lets us slowly dial up the pressure into the regime where hydrogen stops behaving like a gentle gas and starts turning weird. Then, scientists fire powerful lasers through the diamonds, heating the sample to thousands of degrees. For a brief moment, that pinprick of matter lives in conditions strikingly close to Jupiter's metallic hydrogen layer. So what happens in there? You know the one, the claim you've seen in headlines. Metallic hydrogen created in the lab. Several teams have reported that at around a couple of million atmospheres, hydrogen suddenly becomes shiny and reflective, and its electrical conductivity shoots up. Light bounces off it like off a liquid metal. That's exactly what our models predict for the shell that powers Jupiter's magnetic field. Is it universally accepted? Not yet. The experiments push diamonds, optics, and theory to their breaking point, so every result gets argued over. But the evidence is piling up. Then there's the louder, more explosive approach. Instead of squeezing slowly, dynamic compression experiments slam materials with shock waves from high-powered lasers or even carefully controlled explosives. Pressures spike far beyond what static anvils can reach. Temperatures soar, and for a few billionths of a second, the sample passes through the same pressure, temperature path that hydrogen or water would follow on the way down toward a giant planet's core. It's not gentle, but it's incredibly revealing. All of this isn't just for a prettier picture in a textbook. These experiments are how we pin down equations of state, the precise relationships between pressure, temperature, and density that tell us how matter packs itself under enormous gravity. Change the equation of state for hydrogen just a little, and Jupiter's predicted core mass, radius, even its internal heat, flow all shift. Get it wrong, and the whole interior model collapses. And yet something is above the planets. Something is below them. The same equations we test in these tiny, violent experiments decide where those deep layers begin and end. So the next step is to ask a more unsettling question. What if the cores we're chasing aren't solid at all, but are slowly dissolving into the metallic seas around them? What if that dissolving isn't a metaphor at all, but the literal state of Jupiter's heart right now? Juno flew past those cloud tops and tugged on Jupiter with its own tiny mass, and the way Jupiter's gravity pulled back told us something deeply uncomfortable. There's no clean, sharp edge where core stops and envelope begins. We used to picture a neat layout, a compact rock and ice ball in the middle, wrapped in metallic hydrogen, wrapped in the atmosphere you see in telescope photos. You know the one. a textbook cross-section with colored rings and a solid dot at the center. But Juno's gravity measurements only fit if the heavy elements gradually increase toward the center, smeared out over maybe half the planet's radius. It's less a marble in the middle, more a fog of weightier material fading into the metallic sea. Because here's what nobody tells you. At tens of millions of atmospheres of pressure and tens of thousands of degrees, rock and ice stop behaving like anything you'd recognize. At those depths, hydrogen is metallic, an electrically conducting fluid. Silicates, water, ammonia, all the ingredients of a classic core can dissolve into that metallic hydrogen the way salt dissolves into water. The result is a blurry boundary. Is that layer still the core if it flows, mixes, and conducts like a metal ocean? This is what scientists mean by a diluted core. Not a tiny, dense sphere, but a broad region where heavy elements are mixed through a huge fraction of Jupiter's interior. Imagine diving down from the clouds, first the familiar atmosphere, then deeper into compressed molecular hydrogen, then into metallic hydrogen that slowly grows richer in oxygen, silicon, iron, and other heavy atoms as you fall. No sudden wall, just a compositional gradient that gets more extreme with depth. How do you end up with a ghost core like that? One idea is violence. Early in the solar system, a giant impactor, something several Earth masses, could have slammed into young Jupiter, shredding its original compact core and stirring those heavy elements outward. Another idea is patience. Over billions of years, slow convective mixing and double diffusive layering could have gradually eroded the core, letting metallic hydrogen eat away at it. Or the core might never have been sharply defined at all, if Jupiter formed by gently gathering icy, dusty pebbles that dissolved as they sank. Now, let's begin to rewrite what the word core even means. We like to imagine a solid ball, a planetary nucleus you could stand on if you were somehow immune to the pressure. But in a diluted core is less an object and more a pattern, a gradient in composition, not a physical surface. It's like discovering that the bullseye of a target is made of the same paint as the rings around it, just in higher concentration. So when we say Jupiter has a core, we're really saying it has a central region where gravity has hoarded heavy elements, spread out and partially dissolved. That challenges our intuition, but it also opens a door. If a core can be fuzzy here, what about Saturn, or the ice giants, or even giant exoplanets we'll never visit? Because once you accept that a core can be a gradient instead of a granite sphere, the interiors of giant planets stop looking like simple layer cakes and start looking like evolving, three-dimensional chemical landscapes. And the next question is obvious. How do those strange blended hearts change the way these worlds shine, spin, and generate their magnetic fields? So if Jupiter's heart is this smeared-out diluted ghost, what about the other giant we always draw right next to it? You know the one, with the rings that hijack every solar system poster. Now, let's begin with what Cassini actually did for Saturn. During its final orbits, the spacecraft threaded the gap between the rings and the planet, and Saturn's gravity tugged on it ever so slightly. Those tiny changes in the spacecraft's motion let us map how mass is arranged inside. And because here's what nobody tells you, that invisible gravity fingerprint hints that Saturn's core is sharper, more compact, and more distinct than Jupiter's. Not a neat marble, not a granite ball, but not a fully dissolved blur either. The numbers are wild. Most models put Saturn's core at around 15 to 20 Earth masses of heavy elements, buried under hundreds of millions of meters of hydrogen and helium. Rock and ice that would float in the outer solar system are crushed into exotic, ultra-dense forms near the center. where pressures may reach tens of millions of atmospheres. If you could somehow hold a spoonful of that material at normal pressure, it might outweigh a skyscraper. You won't, of course, because gravity wins. But the picture matters. Cassini's gravity data suggests that a lot of that mass is confined to a relatively compact region, rather than smeared across half the planet the way Jupiter's seems to be. In other words, Saturn looks more like it has a recognizable core zone wrapped in gradients, instead of gradients all the way down. That alone tells you these two gas giants did not live identical lives. But even Saturn doesn't get a clean boundary. Deep in its metallic hydrogen layer, helium is thought to separate out and fall inward as helium rain, releasing extra heat as it sinks. Saturn actually glows with more energy than it receives from the Sun, in part because of that storm of invisible droplets. As helium and other elements migrate, they blur the outer edge of the core region, mixing heavy elements upward into the metallic hydrogen shell. The line between core and envelope becomes a foggy transition, not a cliff. So why is Jupiter more diluted while Saturn hangs on to a tighter heart? Was Saturn built a little later, when the protoplanetary cloud had already changed composition? Did it form slightly farther out in the disk, where ices were more abundant and easier to pile into a solid seed? Or did Jupiter take a harder hit early on, a giant impact that shattered and stirred its original core until gravity could only rebuild a gradient? Because once you lay these two side by side, the word core stops feeling like a single idea. Even among twin-looking gas giants in the same plane, you get different architectures, different gradients, different ways to hide heavy elements under a sea of hydrogen. And yet something is above the planets. Something is below them. If Saturn and Jupiter can have such different hearts, what does that do to the way they spin, shine, and carve out their magnetic bubbles in space? And what happens when we look at worlds that aren't gas giants at all? To see how wild that question really gets, we have to leave the gas giants and drop in on the so-called ice giants. Uranus and Neptune look like the quiet, distant cousins in a family portrait. But inside, they might be the strangest of them all. Because here's what nobody tells you. Most of their mass isn't in a Jupiter-style hydrogen envelope at all. It's in a deep, crushing mantle of what planetary scientists still call ices, even though nothing there is anything like the ice cubes in your freezer. Think water, ammonia, and methane pushed so far beyond normal that they turn into hot, dense, electrically conducting fluids. You're not swimming in an ocean. You're falling through a superheated, supercritical chemical soup. So, let's start at the very beginning of their interiors. At the very center, models suggest there's a relatively small but brutally dense rock metal core, just a few Earth masses across, made of silicates and iron and whatever heavy elements gravity could hoard. Around that, instead of metallic hydrogen like in Jupiter, you get this enormous ice mantle that holds the bulk of the planet's weight. In terms of the whole planet, the core is smaller, but the icy layer above it is massive. Here's the twist. That rock metal core might actually be more sharply defined than Jupiter's ghostly, diluted heart. Why? Because the mantle above it is compositionally distinct. Hydrogen and helium blur smoothly into each other. A mantle dominated by water, ammonia, and methane derivatives does not. That contrast in composition acts like a boundary line. In a cross-section picture, Jupiter's center looks smudged. Uranus and Neptune may have a crisper, more abrupt transition from exotic fluid to concentrated rock and metal. And yet something is above the planets. Something is below them. Even out here, central pressures still reach millions of atmospheres, with temperatures of thousands of degrees. That's less extreme than Jupiter's 70 million atmosphere inferno. but it's still enough to crush molecules, strip electrons, and push water into bizarre regimes like supersonic ice, where oxygen atoms lock into a lattice while hydrogen ions roam through like an electric current. Is that a solid? A liquid? Both at once? Here's your pattern interrupt. Their magnetic fields don't behave. Uranus's field is wildly tilted and lopsided. Neptune's is offset from the center. That's a clue that the dynamo, the churning, conducting region where magnetic fields are born, sits not right at the core boundary, but higher up in the ice mantle itself. You get a planetary magnet powered by a shell of exotic water chemistry. So what is that central core really like? Solid iron rock? Partially molten? Some mixed quantum weird phase we don't fully understand yet? For now, it's an open question, and it sets the stage for an even deeper mystery. What happens when you go beyond ice giants to worlds that never see starlight at all? So let's push that mystery to the limit. We get tiny comets and ice shards. What if a whole Earth mass world, a rogue planet drifting through interstellar space, slams straight into Jupiter? Now, let's begin with the approach. This incoming Earth isn't gently parking in orbit. It's dropping into Jupiter's gravity well at tens of kilometers per second, faster than anything you've ever seen re-enter an atmosphere. From far away it looks calm, almost slow. Then it hits the cloud tops, and the picture changes instantly. At the very top of Jupiter, air is thin, but at those speeds, thin doesn't help you. A bow shock forms in front of the falling planet, heating gas to thousands of degrees. Rock, oceans, crust, atmosphere on the rogue Earth all start to glow. You know the one? Those textbook images of a meteor burning up? Scale that up until the meteor is an entire world. Because here's what nobody tells you. Long before this Earth reaches anything like a surface, Jupiter fights back. Atmospheric drag slams into the leading face, raising pressures to millions of atmospheres as it drives deeper. The outer layers shear off. Continents peel away. Mountain ranges get shredded into incandescent vapor. The planet doesn't hit Jupiter like a billiard ball. It's sandblasted into a trail of superheated fragments stretching thousands of kilometers down. Those fragments keep falling. Gravity won't let them stop. As they plunge through denser and denser layers, compression ramps up the temperature again. Silicate rock melts, then boils. Iron cores don't stay as neat metal balls. They're squeezed, ionized, stripped into exotic fluids. Eventually, hydrogen around them crosses the threshold into metallic hydrogen, a churning, electrically conducting ocean that behaves less like air and more like a liquid metal sea. In that metallic layer, the remains of our Earth dissolve. Literally, heavy elements mix into Jupiter's deep interior, the way salt disappears into water, turning what once were sharp boundaries into blurred gradients. Some of those heavy elements will keep sinking, pulled toward the deepest regions by gravity. Others spread out, thickening that inner envelope so that the core becomes a fuzzy, diluted zone rather than a clean ball. And yet something is above the planets. Something is below them. Giant worlds sit in the solar system's flat orbital plane, but inside they're swallowing other worlds and rewriting their own centers. Each impact like this would quietly grow Jupiter's heavy element budget, rearrange its layers, and stir its metallic hydrogen dynamo. So, let's start at the very beginning of the next question. If giant planets can eat Earth-sized worlds, what does that do to the cores of even larger, darker giants that never orbit any star at all? Those dark giants drifting between the stars sound like perfect hiding places, right? A whole planet with no sunrise, just endless night and a deep, secret core. So the obvious question is, could anything survive down there? Now, let's begin where the idea of life in a giant planet actually has a fighting chance. Not in the core, but high above it, in the upper atmosphere. There's a narrow band where temperature and pressure slide past Earth-like values for a moment. You know the one. Not too hot, not too cold. A few bars of pressure, plenty of chemistry swirling in the clouds. People have speculated about floating organisms in Jupiter's skies, balloon-like life that rides convection cells the way jellyfish ride ocean currents. It's a wild picture, and it might not violate physics. But as you fall deeper, the rules change. Fast, the gentle cloud decks give way to a crushing ocean of hydrogen. Gravity ramps the pressure up to hundreds, then thousands, then millions of times what you feel at sea level. Temperatures shoot past the melting point of rock, then steel, then diamond. Because here's what nobody tells you. By the time you're approaching the metallic hydrogen layer, the idea of familiar chemistry is already in trouble. Complex molecules, the long, fragile chains that make up proteins, cell membranes, don't just struggle there, they're ripped apart. Every collision is high energy. Atoms smash together so violently that bonds can't stay intact for long. Electrons get stripped off, then slammed back on, then stripped again. It's like trying to build a sandcastle in the middle of a jet engine. Could you have biochemistry in that environment? Where would it even store information before the next impact tears it to shreds? Push a little deeper and hydrogen turns metallic, electrons move almost freely, and the planet behaves less like a chemical soup and more like a giant conducting fluid. Ionization isn't a rare event. It's the default state. The core regions don't care about molecules. They care about quantum mechanics and pressure. Matter there is closer to plasma or a degenerate fluid than anything you'd recognize from a lab beaker. Even stable atoms are being squeezed, distorted, forced into arrangements that ignore the periodic table's polite rules. So yes, giant planet interiors are extraordinary laboratories for physics. They teach us how gravity sculpts matter, how magnetic fields are born, how exotic phases like metallic hydrogen actually behave. But as cradles for life, as we know it, they're not just hostile, they're fundamentally incompatible. And yet something is above the planets. Something is below them. If the cores are sterile, that just shifts the real mystery. We're in this layered, three-dimensional picture of planets and space, with the strangest forms of matter, and maybe the strangest habitats, actually hide? So if giant planet cores are already this alien, what happens when you keep turning the dial? Push the pressures higher, the temperatures hotter. Where does this ride actually end? Because here's what nobody tells you. The core of Jupiter is not some special, isolated category. It sits on a sliding scale that runs all the way from fluffy planets to crushed stellar remnants. Change the mass, and gravity rewrites the rules of matter, step by step. Now, let's begin with the next rung up from our familiar gas giants. Imagine a super Jupiter, 10, 20 times Jupiter's mass, still orbiting some distant star. From the outside, it might look like a slightly oversized planet. But inside, the gravity is brutal. Central pressures soar past what Jupiter can manage. Temperatures rocket upward, and hydrogen is squeezed so hard that metallic hydrogen isn't just a shell, it can dominate the entire interior. Keep going, and you hit brown dwarfs. You know the one, the so-called failed star. Too small to ignite long-term hydrogen fusion like the Sun, but far more extreme than any planet. In their cores, Gravity pushes temperatures to millions of degrees. For a while, they can fuse deuterium, and the most massive ones even flirt with brief hydrogen fusion. It's like the universe is trying to light a match and getting only a sputtering flame. Planet? Star? The labels start to wobble. Then the pattern really breaks. Take a white dwarf. Now the mass is crammed into something Earth-sized. Gravity has gone so far that electrons are forced into an electron-degenerate state. A quantum pressure propping the whole thing up. A teaspoon of white dwarf material would outweigh a skyscraper. Go further to neutron stars, and gravity crushes electrons into protons, leaving a sea of neutrons so dense that a sugar cube of it would outweigh a mountain range. Compared to that, even the wildest giant planet core looks almost gentle. Its pressures may reach tens of millions of atmospheres, hot enough to melt diamond and forge metallic hydrogen and superionic ices, but not yet enough to break atoms into a quantum-degenerate fluid. The electrons are still mostly behaving like electrons. The matter is exotic, yes, but it's not in the same league as a white dwarf or neutron star. So, let's start at the very beginning of the question that should now be bothering you. Where does a planet end and a star begin if their cores live on the same continuum of pressure and temperature? Is it about fusion, about mass, about how flat your orbit diagram looks in a textbook, or about what gravity is secretly doing in the dark? Hold that thought, because to answer it, we have to zoom back into the cores themselves and watch how they form, dissolve, and maybe even migrate. So if gas giant cores and stellar cores live on a continuum, you have to ask a dangerous follow-up. What happens when you take a giant planet and park it right next to a star? Not in a comfortable, wide orbit like Jupiter's, but skimming the stellar surface on a blistering, tight leash. Now, let's begin with the celebrities of exoplanet catalogs. Hot Jupiters. You know the one from every artist's impression. A bloated, striped world, hugging its star so closely that a year lasts a few days, with cloud tops heated to well over 1,000 degrees. In some cases, the side facing the star glows as hot as a red dwarf. These are still gas giants, still ruled by gravity and pressure. But the boundary conditions are completely different, because here's what nobody tells you. When you roast a gas giant from the outside in, you don't just bake the clouds, you rewrite the interior. Intense stellar irradiation puffs up their atmospheres, like a balloon held over a flame, making the whole planet look oversized for its mass. The average density drops. The outer layers become more inflated, more extended, and that changes how heat leaks out from the core, which in turn reshapes the temperature profile all the way down. Picture Jupiter's interior as a relatively compact stack: clouds, molecular hydrogen, metallic hydrogen, then a fuzzy, diluted core. Now put that picture on a hot Jupiter. Some models suggest that when a giant planet forms farther out, builds a hefty rock and disk core, and then migrates inward, tidal forces, and furious heating strip, and stir the envelope while leaving a more compact, sharply defined core behind. In other scenarios, the opposite happens. The core erodes and mixes upward, but the outer layers are so inflated that compared to Jupiter, the central regions still end up more tightly packed in relative terms. We can't crack these worlds open, so how do we know anything about their insides? We play a detective game with gravity and light. Measure a planet's mass from how it tugs on its star. Measure its radius from how much starlight it blocks when it crosses the stellar disk. Combine the two, and you get an average density that whispers clues about the interior. Then you add atmospheric spectra, sodium lines, water vapor, hints of metals and clouds being torn by stellar winds. all feeding into models of how heat moves from the surface down to the deep core. And yet something is above the planets. Something is below them. In this case, above and below are different regimes of pressure and temperature that we can only infer. Studying dozens, then hundreds, of exoplanet giants in different orbits lets us test how cores form, mix, and survive. Which ones keep their compact hearts? Which ones dissolve into planetary smoothies? Hold on to that question, because the next step is to ask how far a core can be stretched, blurred, or even erased before the planet itself stops being a planet at all. So here's the twist. That core we keep talking about, it might not stay a neat little marble at the center forever. Because here's what nobody tells you. Under the pressures and temperatures inside a giant planet, our everyday categories break. Rock doesn't have to stay rock. Ice doesn't have to stay ice. At tens of millions of atmospheres, in tens of thousands of degrees, the same materials that make mountains and frozen oceans can become soluble in metallic hydrogen, or in those wild supercritical fluids that don't know if they're liquid or gas. Picture the deep interior of Jupiter as less like layers in a cake, and more like a slow boiling cauldron. Metallic hydrogen churning, heat leaking outward, gravity trying to keep heavy elements sunk in the middle. Now, let's begin to mess with that picture. If silicates, iron, or ices can dissolve into that metallic ocean, the sharp boundary between core and envelope starts to blur. What used to be a compact heart becomes a fuzzy, diluted region where heavy elements are smeared out over a huge volume. How does that smearing actually happen? Convection is the first culprit. Hot material near the core expands, becomes slightly less dense, and rises. Cooler material higher up sinks. Over billions of years, that slow overturning can drag dissolved heavy elements away from the deepest center and mix them into the overlying layers. But it's not just simple stirring. In many models, you get double diffusive mixing, where heat and composition diffuse at different rates. You end up with staircases of semi-stable layers, each one slowly leaking heavy elements upward like a planetary lava lamp. Juno's precise gravity measurements suggest Jupiter's core is not a tiny, sharp ball, but a diluted core spread across maybe half its radius. You know the one, the textbook diagram with a clean raucous sphere in the middle? That might describe baby Jupiter. The adult version could have started with a more compact core that has been eroding, dissolving, and bleeding its heavy elements into the envelope for 4.5 billion years. And yet something is above the planets. Something is below them. The same gravity field that defines the ecliptic plane of the solar system also lets us sense these hidden interiors, tiny deviations in a planet's gravitational harmonics, subtle enrichments of elements like carbon, nitrogen, or heavy noble gases in the atmosphere, even quirks in the magnetic field. All of these are indirect fingerprints of long-term core erosion and mixing. But the core isn't just a static ball at the bottom of a planetary ocean. It's part of a dynamic interior ecosystem where heat, composition, and exotic phases of matter interact. Over time, that ecosystem can turn a once solid heart into a gradient, a blur, a ghost. The real question is, if you keep eroding a core, dissolving it, stretching it out, at what point does the planet's identity itself begin to change? Hold that thought, because the next layer down may be stranger than a missing core. So let's pull that familiar picture back up. You know the one. The neat circular planet sliced open like a cosmic onion, thin atmosphere, bright outer shell, darker middle, tiny glowing core, sitting perfectly in the center, like a prize at the bottom of a cereal box. It looks satisfying. It looks clear. It's also lying to you in about 5 different ways at once. Because here's what nobody tells you. Those razor-sharp lines between layers, those are graphic design decisions, not discoveries. In a real giant planet, there isn't a single altitude where hydrogen suddenly flips from gas to liquid to metallic like a light switch. Pressure ramps up, temperature ramps up, and the molecules get squeezed through a whole spectrum of weird behaviors. The diagram has to pick a boundary. Nature does not. Look at the colors. A calm blue for the atmosphere, a bold silver ring for metallic hydrogen, a neat brown dot for the core. That palette quietly tells your brain, these are separate things. Solid, liquid, gas, metal done. But inside Jupiter or Saturn, those categories melt into each other. The atmosphere thickens until it behaves like a fluid. The liquid hydrogen becomes so compressed it conducts electricity. Deep ices in Uranus and Neptune turn into superhot, supersonic phases that don't fit our everyday words at all. So, let's start at the very beginning of how we draw these. When scientists build an interior model, they're turning messy data, gravity measurements from Juno, magnetic fields, seismology, lab experiments that crush hydrogen to millions of atmospheres, into something you can glance at in a textbook. They choose where to put lines, what to call each region, what color means conducting, what color means molecular. Those choices are metaphors. They are not literal maps of where one phase ends and another begins. Here's the pattern interrupt. Next time you see a cross-section, try a mental hack. Blur the edges. Let the tidy metallic hydrogen shell bleed upward into the molecular layer. Let the core smear outward into a diluted region where heavy elements are mixed with lighter ones. Ask yourself, is this a wall? Or is this a zone? Is this a surface? Or is this a gradient stretched over tens of thousands of kilometers? Because once you do that, those diagrams stop being lies and start being what they really are. Snapshots of a three-dimensional, evolving interior. And yet something is above the planets. Something is below them. Not in the sense of flat layers on a page, but in the sense of deeper pressures, stranger phases, more extreme gravity as you move toward the center. This is the meta lesson of astrophysics. Almost every simple picture, the flat solar system, the sliced open planet, the clean core at the middle, hides a turbulent, three-dimensional reality underneath. Hold that in your head, because when we dive into the next layer, we're going to lean into the gradients and watch those clean lines fall apart. So if those clean lines fall apart, what happens to the cleanest line of all? The one that says here is the core. We talk about the core of Jupiter or Saturn like it's a steel ball bearing you could hold in your hand. But is a core a place, a composition, a density threshold, or just the innermost region where certain processes win the tug-of-war? Because here's what nobody tells you. Core is a shortcut. It sounds like a single point, a dot in the middle of a diagram. In reality, inside a giant planet, it's much more like a zone where gravity, pressure, and chemistry gradually change the rules. So, what are we really pointing at when we say Jupiter's core in the first place? Now, let's begin to stretch that word. Imagine diving down through Jupiter. At first you're in hydrogen and helium, the normal gas you see in the textbook picture. Deeper in, that hydrogen compresses into a dense liquid, then into metallic hydrogen that behaves like a conducting metal. Keep falling, and the fraction of heavier elements, oxygen, silicon, iron, quietly climbs. You never hit a crisp border. You move along a spectrum. So, let's start at the very beginning of a new mental model. Instead of gas, shell, solid ball, think continuously increasing concentration of heavy material as you go inward. At the very center, that material might be almost pure rock and ice. Above that, it's mixed into metallic hydrogen. Above that, mixed into molecular hydrogen. The core is not a discrete object. It's the inner part of this gradient where heavy elements dominate the mass and the behavior. And yet something is above the planets. Something is below them. We accept that with orbits and the solar system's flat plane. But inside a giant planet, we resist the same idea, that there can be an above and below the core region without any sharp floor. Juno's measurements of Jupiter's gravity hint that its heavy elements are smeared out over half the radius. Is that a core or a dissolved memory of one? In some worlds, the shortcut still works fairly well. Uranus and Neptune probably have a more compact, ice-rich region where properties change faster with depth, so the word core feels closer to a place. In others, like Jupiter, it's more honest to talk about a core region, a gradient of increasing density and heavy element fraction, rather than a billiard ball. Why does this matter for evolution and collisions? Because if a core is a process zone instead of a rock, then a giant impact doesn't just crack or displace a solid object. It can stir, dilute, or even partially erase that gradient. A hit early in Jupiter's life may have mixed heavy elements outward, helping create the fuzzy core Juno sees today. But when you hear core and future discoveries, inside planets, moons, even stars, try this more flexible definition. Ask, what process dominates there? What gradient is being summarized by that one word? In the next layer down, we'll lean into that question and watch how a core can melt, mix, and reassemble over billions of years. And here's where things collide with something much closer to home: your own intuition. We've just turned core into a process and a gradient, not a neat little ball. That feels wrong on a gut level, doesn't it? Because you and I grew up in a world of floors and walls. You stand on the ground, you bump into the table. You know the one, the world where every important thing has a clear edge. So when we drop you into Jupiter and tell you there is no real surface, your brain quietly rebels. It keeps asking, okay, but where do I land? Where's the bottom? Because here's what nobody tells you. Almost all of your physical intuition was trained on solids. Dry land. Sharp boundaries. From the time you could walk, gravity pulled you toward a hard surface, and that surface stopped you. Your eyes learned to track horizons. Your hands learned that doors separate inside from outside. Even a swimming pool has a floor just a few meters down. You live inside a universe of edges, so you instinctively look for something to stand on. Now let's begin to notice how that bias sneaks into our language. We talk about surface gravity, as if every world must have a crisp outer shell you could walk across. We say solid core, even for planets we know are molten or mixed or blurred. We call Jupiter a gas giant, which quietly smuggles in the idea that it's just a big balloon of familiar air floating in space. But inside a giant planet, those words start to crumble. The surface is just the altitude where the gas becomes opaque. The core might be a diffuse cloud of heavy elements spread across half the radius. Not a rock you could sit on. Even gas stops behaving like the air in your room once it's squeezed by millions of atmospheres of pressure. So, let's start at the very beginning of a new habit. Try imagining an environment where there are no true surfaces at all. Only continuous fluids. Only gradients. Density slowly rising. Temperature slowly climbing. Hydrogen smoothly morphing from gas to liquid to metallic fluid without a single moment where you could knock on it and say, "Here, this is the wall." And yet, something is above the planets. Something is below them. Fields, pressure, flows, much of modern physics lives in that kind of world. where our everyday pictures fail and we have to build new mental models from scratch. So what happens when we fully commit to that view and follow it all the way down into a giant's heart? That's where things get really strange. So if there are no hard walls inside a giant planet, no neat shelves of rock, where is down supposed to be? When you're falling through clouds that never end, what are you even falling toward? Now let's begin with a quiet cheat code of physics. Down is not a universal direction. It's just the way gravity is pulling you right now. Stand on Earth, and down points toward Earth's center of mass. Hover above Jupiter, and down suddenly swings toward Jupiter's center. Drift alone in deep space, far from any planet or star, and down disappears. Because here's what nobody tells you. Direction is local. It belongs to the nearest gravity well. Inside a giant planet, that gets even stranger. There's no staircase, no mountain slope, no preferred tunnel to the core. Every direction that points toward the center of mass is equally down. If you could pause the whole planet and draw arrows on the gas, every arrow would lean inward, like a three-dimensional hedgehog of gravity. Pick any spot, any angle, dive in. As long as you're curving toward the center, you're going down. That means our usual language of height and depth starts to wobble. There is no below the equator versus above the equator in any absolute sense. That's just us picking a rotation axis and pretending it's special. Rotate the whole picture, and what was north becomes sideways without the planet caring at all. The gas doesn't see a map. It only feels the pull. So scientists quietly retire words like up, down, high, low, and reach for a different toolkit. Radius, pressure, gravitational potential. Instead of asking, how deep are we? They ask, how far are we from the center? What's the pressure here? How much energy would it take to climb back out? A point 30,000 kilometers from the center with a pressure of 1 million atmospheres is more meaningful than saying really far down. You know the one, those textbook cross-sections that show a bold line labeled core boundary, as if there's a painted stripe inside Jupiter. In reality, that boundary is usually defined by a threshold we choose, maybe where hydrogen turns metallic, maybe where the density crosses a certain value, maybe where the mix of rock, ice, and hydrogen shifts past some percentage. Change the criteria, and the edge of the core quietly moves. This is the pattern we keep running into. Our diagrams draw tidy rings. Nature gives us continuous gradients. Our words carve sharp borders. The planet offers smooth transitions. What we're really doing is laying a coordinate system over a blur so we can talk about it without losing our minds. And yet something is real underneath those lines. The way pressure climbs, the way phases of matter change, the way gravity shapes every orbit of every particle. So what happens when we stop staring at the map and follow those invisible coordinates all the way into the most extreme layers a giant planet can hide? So let's rewind the picture in your head for a second. You know the one. A perfect ball of colored gas, sliced open like a science fair model, tidy pastel bands, then a sharp line, then a dense rock core sitting in the middle like the pit of a peach. Clean layers, clear borders, an onion in space. Because here's what nobody tells you. That old diagram is less a planet and more a filing cabinet. It's how we sorted ideas, not how gravity actually arranges matter when you squeeze it tens of millions of atmospheres deep. Inside a real giant, there isn't a polite gas layer that hands things off to a neatly labeled core. There's a continuous crush of pressure that slowly mutates everything as you fall. So, let's start at the very beginning of this new model. Imagine dropping through the clouds of Jupiter or Saturn. At first, it does look like the cartoon. Hydrogen and helium gas swirling in stormy bands. But keep falling. The gas thickens until the word gas stops making sense. Molecules are jammed so close together that hydrogen turns into a supercritical fluid, something that isn't quite a liquid and isn't quite a gas, filling the planet like an ocean without a surface. Deeper still, that ocean becomes metallic hydrogen, a churning, electrically conducting fluid wrapped around a region enriched in heavier elements. Is that region a solid core? A fuzzy, diluted cloud of rock and ice smeared out by convection? Juno's measurements of Jupiter's gravity hint that the answer is both and neither. The core is not a marble. It's a gradient. And those layers you saw as flat stripes on a diagram? They're not sitting still. They convect. They overturn. In Saturn, helium droplets separate out and rain downward, releasing extra heat as they fall. In Uranus and Neptune, carbon may crystallize into diamonds that sink through a mantle of superhot water and ammonia, only to melt or dissolve again. Over billions of years, those rains and currents can erode that heavy element region, mixing core material outward and blurring the very boundary we tried to draw. Different giants just pick different paths through this landscape of extremes. Jupiter pushes hydrogen all the way to a vast metallic shell. Saturn does the same, but adds that dramatic helium rain. Uranus and Neptune live in the ice giant regime, where supercritical water and ammonia dominate, and metallic hydrogen, if it exists at all, is a much thinner layer. Hot Jupiters crank the temperature dial so high that even their outer envelopes are wildly inflated, their interiors reshaped by relentless starlight. So when you picture a giant planet now, don't see a static ball with a rock in the middle. See a living sphere of extreme physics, gradients instead of borders, processes instead of parts, a core that is more verb than noun. Because once you let that image settle in, you're ready for the next question. How do we read these invisible interiors from nothing but a planet's light, its magnetic field, and the tiniest wobbles in its orbit? So here's the twist. For all that talk about gradients and invisible layers, the cores of giant planets are still, in a very real sense, educated guesses wrapped in gravity data. We can tell you Jupiter is massive, that its gravity field is lopsided in just the right ways to hint at a diluted core. But is that core a fuzzy, slowly fading smear of heavy elements, or is there still a compact kernel buried deep inside that blur? Saturn might hide a similar hybrid interior. Uranus and Neptune, those so-called ice giants, raise their own question. Do they even have sharply defined cores at all? Or do their rock and ice just thicken continuously toward the center until the word core stops making sense? Because here's what nobody tells you. When we say Jupiter's core might be 10 Earth masses, or Neptune's core could be 15, we're not reading off a label. We're solving equations that depend on how hydrogen, helium, water, ammonia, and rock behave at millions of atmospheres. Change the equation of state for hydrogen at 70 million times Earth's pressure, and the same gravity data can be explained by a heavier core or a lighter one that's more spread out. Those equations of state are where the uncertainty really bites. Compress hydrogen in a lab with diamond anvils and lasers, and you get one picture. Simulate it with supercomputers, and you get another. Push water into superyonic phases that conduct electricity and blur the line between solid and liquid. And suddenly, Uranus and Neptune's interiors can be drawn 3 different ways from the same magnetic field. On top of that, the cores themselves might not be staying put. Over billions of years, high-temperature, high-pressure weather can erode a one-sharp boundary, dissolving rock and ice into metallic hydrogen and slowly mixing heavy elements upward. How fast does that erosion happen? How far do those elements climb before gravity drags them back down? And how often does a giant impact, another world-sized body slamming in during formation, reset the whole interior, stirring the core like a cosmic spoon? Now let's begin to look forward. Juno's extended mission at Jupiter. New gravity maps of Saturn from Cassini's final orbits, and future probes to the ice giants will tighten the error bars. Telescopes like JUICE are already measuring the heat leaking from exoplanet interiors, while next-generation lab experiments try to recreate metallic hydrogen and supersonic ice more cleanly. Each new constraint can kill off whole families of interior models in a single stroke. And yet something is above the planets. Something is below them. The real cores of giant planets sit just out of reach, waiting for the next measurement that forces us to redraw the whole picture. So what happens when the data finally disagree with our favorite model, and the planet itself tells us we've been wrong about its heart this whole time? So what happens if we stop guessing from the outside and actually fall in? Not with a probe, not with a submarine, but with your imagination strapped in and the safety settings turned off. Now let's begin at the only surface a gas giant really has, the cloud tops. You're hovering above that banded picture you've seen 1,000 times, the colorful swirls of ammonia and water clouds racing around under low gravity, lightning flickering in storms the size of continents. Up here, the air is thin, the sunlight is bright, and it still feels like ordinary sky. Then you let go. You start dropping through the upper atmosphere, past familiar white and orange clouds into deeper reds and browns. The pressure builds, the wind howls sideways, and the temperature climbs from chilly to sauna to furnace in a matter of hundreds of kilometers. Hydrogen and helium thicken around you. The clear air turns into a dense, hot fog. Because here's what nobody tells you. Long before you reach the inside, you've already lost every intuitive sense of what air and liquid even mean. Keep falling. At a few hundred kilometers down, the distinction between gas and liquid vanishes. You plunge into a supercritical ocean of hydrogen, a state that isn't quite a gas, isn't quite a liquid, but both at once. There's no surface to splash through, no clean boundary, just a smooth, relentless increase in pressure as the weight of the planet piles up above you. You're still in free fall, but the drag is enormous, like trying to skydive through boiling syrup. Deeper still, the color drains away. Sunlight is gone. The only glow is the planet's own heat, infrared radiation from below. Temperatures roar past thousands of degrees. The hydrogen around you is squeezed so tightly that electrons start to roam freely, and you cross into the metallic hydrogen ocean. It looks dark and featureless, but it behaves like a liquid metal, conducting electricity and feeding the vast magnetic field that reaches out into space. As you fall through this metallic shell, the density climbs toward that of solid rock, then beyond. Heavy elements become more common in the mix: oxygen, carbon, silicates. Maybe a rain of helium droplets sinking past you like ghostly, incandescent hail. The core no longer feels like a separate object. It's a gradient of more and more exotic matter. So, let's start at the very beginning of your expectations and throw them out. What does solid mean when pressures reach tens of millions of atmospheres and temperatures rival the surface of a star? At some depth, the atoms themselves are so compressed that our everyday categories fail. We're left with equations, shockwave experiments, and the planet's gravity and magnetic fingerprints to guide us. Keep going one last time. You approach the very center, not a glowing crystal ball you could stand on, but a region defined by limits of pressure, of temperature, of the physics we've actually tested. There's no view here, no horizon, just the point where all directions cancel and gravity pulls equally from every side. The true core isn't a place you could ever visit. It's the invisible anchor of the entire planet. The part that forces us to admit how much of the interior we still have to learn. So if the true core is an invisible anchor instead of a solid throne room, what have we actually uncovered on this dive? We've met a planet interior that refuses to sit still. Metallic hydrogen oceans, helium rain, diamond storms, diluted ghosts of cores and compact, crushing centers, all sharing the same world. That's not a neat diagram. That's a living, shifting machine. Because here's what nobody tells you. Once you go inside a giant planet, the simple picture collapses. You don't just have gas on the outside, rock in the middle. You have hydrogen squeezed until it flows like a liquid metal and carries electric currents that power planetary dynamos. You have helium separating out inside Saturn and literally raining down, releasing heat as it falls. You have Uranus and Neptune hiding mantles of superhot ices and, deeper in, pressures where carbon can crystallize into falling diamonds. How do you even draw that on a flat page? And yet something is above the planets. Something is below them. Even in a system with no hard surfaces, there are still centers that quietly run the show. Those fuzzy cores, those gradients and mixed layers, they decide how strong a planet's magnetic field will be, how much heat leaks out, how fast the whole world cools and churns. They help set which moons can keep subsurface oceans, which orbits stay stable, which regions of a planetary system are safe or chaotic. No surface, but enormous consequences. So let's start at the very beginning and zoom back for a second. Every one of these extremes began as a tiny seed inside a collapsing cloud. You know the one, a cold, dark region of gas and dust where gravity wins and a disk forms. In that disk, pebble-sized grains and icy boulders collided, merged, and built the first cores. Those seeds didn't stay polite. They swallowed gas, ice, and in some models, entire other planetary embryos, growing fast enough to drag in whole envelopes of hydrogen and helium. Now those early cores have evolved into something stranger. Our old mental model was a simple solid ball at the center, like a marble in a fog. Now, let's begin again with a different picture. Cores that can dissolve into the layers above, forming vast diluted regions, boundaries that are not sharp lines but thick transitional zones, interiors ruled by gradients, mixing, and exotic physics we're still trying to recreate in the lab. The core is no longer a single object, it's a process. And the wild part? Our solar system might be the tame version. As we discover more exoplanets, we keep finding hot Jupiters skimming their stars, mini Neptunes packed into tight orbits, worlds with densities that make no immediate sense. If Jupiter's core can blur into a metallic hydrogen ocean, what happens inside a planet twice as massive, or 10 times hotter? Are their cores made almost entirely of superionic water, or shells of metallic hydrogen wrapped around shrunken rocky hearts, or something we don't even have a name for yet? Because once you realize how far our picture has shifted, you start to see the next question forming. If giant planet cores can be this weird, what are they still hiding from us in the data we've already taken? So let's turn all of that chaos into one clean picture you can carry around in your head. Not a messy simulation or a blurry diagram, a simple mental model of a giant planet's heart that you can explain at dinner without pulling up a slide deck. Now let's begin with the overall shape. Imagine Jupiter or Saturn or Neptune as a layered sphere of increasingly exotic fluids, not a ball with a solid marble at the center. The outside looks familiar. Clouds, winds, storms. You know the one, the striped globe from every solar system poster. But as you go down, there isn't a sudden floor. There's just more planet, more pressure, more heat. Because here's what nobody tells you. There is no hard surface to land on. No place where your spaceship's landing gear would gently touch down. The gases thicken into fluid. The fluid becomes denser. Atoms are squeezed so tightly that hydrogen stops behaving like a gas at all. You never hit a wall. You just get crushed. So let's start at the very beginning of your dive. First, the visible atmosphere, where hydrogen and helium are still acting like the gases you know from chemistry class. Keep going, and those same elements become a deep global ocean of compressed fluid. Deeper still, in gas giants, that ocean turns into a vast shell of metallic hydrogen, a planet-sized layer of liquid metal that conducts electricity and powers titanic magnetic fields. At the very center of a classic textbook diagram, you'd see a tiny solid core labeled rock and ice. In your new model, that core is not a neat little ball. For Jupiter and Saturn, it's a dense, evolving region of heavy elements, partly dissolved and mixed into the metallic hydrogen around it. Its edges blurred by billions of years of gravity in convection. For Uranus and Neptune, the picture shifts. A thick mantle of hot ices, water, ammonia, methane in supercompressed, superionic, neutrally solid states, wrapped around a more compact, heavier core. If you want to keep falling inward, tap subscribe and let this next video pull you down into another extreme interior. The surface is just the beginning.